Okay, today we'll see the cantilever method in approximate methods. Okay, take a frame like this. So if I apply a transverse load. Okay, some distances. Okay, now some height of the story, some 3, 4, like this. Imagine, just imagine, just convert this frame into this frame into 90 degrees. How it's look like? How it's look like? This is the specimen. It's look like a cantilever. Are understood? So if you see cantilever beam, this is a cantilever beam. Exactly symmetry, na? Symmetry. It's look like a cantilever. Okay. How we analyze this frame in a cantilever method? Exactly how the cantilever beam behaves. Okay. So cantilever beam behaves like this. Okay. So the top layer is in tension, bottom layer is in compression. So that's why if you see it is this tension, this compression, and somewhere this center line, if you take it is this center line, it's neutral axis. Somewhere it has neutral axis. So top layers above the neutral axis is in tension, top below layers is in compression. Clear indication apart from this portal frame method, there is no clear indication regarding tension and compression. We just assume it, not assume, we just feel it is, that's it. Now here it's exactly above the neutral axis in tension, below the neutral axis is in compression. So where is the exactly neutral axis? Where is the neutral axis? That's the question, na? So here where is the neutral axis? So how can you find out the neutral axis? Just like a center of gravity. So something, this distance is some, if you see it is, take a section, take a section, take a section, take a sectional area, something. Neutral axis we can consider into the areas also. This is the only area present in the section. So if some of the columns has different area, so this area is A1, this A2, A3, A4. Areas may be different, may not be different. Maybe sometimes all columns are equal areas. Sometimes in different analysis, outer columns and inner columns may place different areas. So in this cantilever method, areas of the columns take into the consideration of analyzation. But if you see the portal frame, there is no role of areas of the columns in the analyzation of the frame. Okay, so here must and should take into the account of those areas of the columns. So this is A1, A2, A3, A4, and distance is also something like, so x1, x2, x3, this is 0. Y you consider x, you may call it as a y also, but this horizontal axis, now we just think it is in a cantilever in vertical axis. So just I gave x, otherwise you taken as y also. So where is how it neutral axis? Like center of gravity, what is that? A1 x1, A2 x2, A3 x3, A4 x4 divided by A1, A2, A3, A4. That is a neutral axis. Maybe neutral axis will come somewhere. This is x dash. So, okay, that is a neutral axis, and also you can find out the moment moment of inertia of that section moment of inertia, how can area into distance square, that's it na, a1. So the distance is, this is the distance a1. What is the distance? a1 x1 minus x dash square. Area into distance square is the moment of inertia. This distance, what is the distance? a2 into x2 minus x dash square, so on, a3 into x3 minus x dash square. See what is that value? Negative, but not negative square terms. So you can find out the I value. Why we required ix, I will show it. So here if you see the cantilever, what is the stress distribution regarding a section across the section? Stress distribution, if you see this, the stress distribution diagram, top layer in tension, bottom layer is in compression. What is the stress at this location? You already know stress equal to m by I into y, distance from neutral axis. Okay, if you want force, m by I into y multiply with the area of that section. You already know in simple bending theory of any section. Okay, so same consider here. You will consider what is the axial force not stress, force in this zone. What will axial force in this zone? You can find out axial force in this zone, axial force in this zone, axial force in this zone, in this zone, in this zone, in this zone, in this zone. So first we calculate the axial force in columns based on cantilever theory. Simple bending theory. Okay, so how can you calculate? See, take this is the section, this is the column. Here what is the force? Is the tension. These are in tension. What is this force? How can you find out force? Same, just observe it here. What is the, this is the stress. What is the stress? m by I into y. So force multiply with the area. So if you consider this, look like, what is this value? How can you get that value? So we required moment. So what is that moment in this zone? So this is a one force, this is a one force. The moment is variable from this force p into some distance, but this moment is variable in this zone. But we made some assumptions for calculating this force in that zone. We assume, this is assumption, we assume that the moment in this zone is equal. So how can you equal it? Is a variable from p to p multiply with x. X is variable from this to this na. Okay, so we made assumption we will take average moment on that zone. So what is the average? Average is at the center. So what is that moment? So p into this half of that column height. So p into some h. You can calculate moment. That moment is called story moment. So what is the moment in this zone? In this zone also we will calculate average. Average means at the center. You can call it, take as a center. So this is length, force into this distance, this force into this distance. Okay, this p1, maybe this p2, p1 into distance, p2 into distance. Average, that's assumption, not real, that's assumption. Okay, so we calculate m, we will calculate m story moment. This is a second story moment, this is a first story moment. It doesn't change in between these columns. This one column, second column, third column, maybe this is fourth column. These four columns, the moment doesn't change. Moment changes between first story and second story, not change between first column, second column, third column, fourth column, because all are in the same section. See, moment doesn't change. So m By I we calculated. I is like area of y, x minus x dash whole square. So y means the distance x. Y means what? Distance from nodal axis. Distance from nodal axis is what? X minus x dash. We call it as x. Already see it. Distance from the nodal axis and area of that column. This is a force in that column. So you can write like this. Here is my x minus x square divided by x minus x dash divided by area. It's look like m by y. Force equal to moment by distance. This has a distance. A cancel. This cancel. Only distance dimensional formula will arrive. M moment divided by the distance. You can get the force in that column. Are understood? Force in the column, force here, force here, force here, force here, force here, force here, force here. Those forces are axial force in that column. Once you find out the axial force in the columns, remaining shear force, bending moment and axial force in beam will calculated based on equilibrium equations. That's it. I will show one problem. You can understand clearly. Okay, so take a problem. Example. Very small problem. 25, 50. This is 4 meters. This is a 4 meters. This is a 4 meters. This is a 4 meters. And area of the columns also matter in this method. So I will give, this has 2a, a and a. That means area of this column is 2 times the remaining 2 columns. Okay, so how can you proceed? We just turn down the frame into a 90 degrees. Turn down the frame into a 90 degrees. $25, 50. Support 4, 4, 4. Okay, it's a 2a, a. Just imagine it's a cantilever. Find out this nodal axis. What is the nodal axis? Where it is the nodal axis? Just take a section, any section. Take a section. Area. It's a 2a, a. Distance is 4, 4. So write down area into distance. 2a into 8. Area into 4. Area equal to 0. This area into 0. So divided by 4a. What is that value? 16, 20. 16, 20. 20 divided by 4. It's a 5. That means from bottom to, it's a 5. That means it's a 5. That is a nodal axis. Are understood? It's nodal axis. What is the distance between this column? Is 3. What is the distance of this column? Is 1. 3, 5. Okay. What is the I value? I value of the section. So again I will show this nodal axis. 3, 5, 1. So what is I value? Area into distance square. 2a into 3 square. Area into 1 square. area into 5 square. What is that value? 18, 19 plus 25. 19 plus 25 is 44. 44a. I is our over. Now consider this is the first column, this is second column, this is the third column, and this is the second story, this is the first story. This is second story, this is the first story. This is second story, this is the first story. So story moment again is story moment. Second story moment is what? This is the second story. Moment is at center. What is the distance? 25 into 2, 50. Story moment 1, first story at center. You can take it as a center. What is that? This value. What is this thing? 25 multiply with 6, 50 multiply with 2. 50 multiply with 2. 100 plus 150 is 250 kilonewton meter. This is the story moment. Now you can write the forces. Forces in columns. So I will show you. This is the first column. This is the second story. This is the first column, first story. This is the second column, second story. This is the first story. I will write one thing. First one. First column, second story. I will write m by I into y into area. So what is the second story moment? 50. I is same for every section. Doesn't change. 44 meter. Distance from nodal axis is 3. Area is 2a. This has 2a. See, remember? It's 2a. What is that value? 6.81. 6.81. So what is that 6.81? Compression or tension? See, above the nodal axis is tension, below the nodal axis compression. So tension, okay, you may call it as positive or negative, your choice. I will write as a tension. Okay, so now comes to the first column, first floor. First column, first floor. What is the change? I doesn't change, y doesn't change, area doesn't change. Only change is m. Moment is changing. So what is that moment? 250. Distance, area, 5 times. Exactly 5 times. 34.09 tension. Now comes to the F. Second column, second story. What is the moment? Moment second story is doesn't change. Moment of inertia doesn't change. Distance from nodal axis is 1. And area of that column is A. 50 divided by D, 1.13. Is tension or compression? Below the nodal axis is compression. So this column and this column must be in compression. This column is in tension. Clearly explained by cantilever. Way of understanding. Assumption as a cantilever. Okay. There is no clear description in portal frame which columns are in tension, which columns are in compression. We just assumption like first column is in tension, last column is in compression. May we can assume, but in between it doesn't clearly explains which column is in tension, which column is in compression, or how much distance the the columns are in tension or compression. And the method doesn't give exact results. Okay, this is also an approximate method, so don't care about those things. Just do the problem. Okay, so this isn't compression. So you have second column, first story, only changes moment, remaining doesn't change. It's 5 times. You have third column, second story. So 50 divided by 44a, distance is 5 meters. You see, distance is 5 meters, area is A, it will comes to 5.68. First column is 250, only moment change is 28.40. Once you got these values, remaining problem is based on the equilibrium equations. I will show. Okay, I will show how to do the remaining problems. So that for that purpose, you draw first a free bodies of those things. I will draw. Free bodies of columns and beams. Okay, now impose those forces. What is that force? First column, second story, 6.8 and tension. Sanction 6.81. So if it is 6.81, it must be 6.81 because should be equilibrium of that column. Okay, so this value, first story, second column, it's 34.09. It's 34.09. Here it's compression. What is that value? 1.13. Compressive direction 1.13. It's also a compression 5.68. 5.68. Here compression 5.68. 5.68. Here compression 28.4. 28.4. These things we already calculated. So now impose on the free body diagram. So remaining forces we calculated based on these things and based on equilibrium equations. Okay, based on equilibrium equations. So first thing we should do is axial force in column. Second thing is shear in beam. How can you calculate shear in beam? See, it is 6.81. Must be this is 6.81. Joint equilibrium. This is a joint. You may consider this is a joint. Joint must be in equilibrium. Beam must be in equilibrium. Column must be in equilibrium. As a part or a whole, you already know. Only based on equilibrium, this structure, our system is moving. Not moving. The system is unstable. So this is 6.81. This is 6.81. This must be a 6.81 because there is no external load in this frame. There is no external load in this frame. Are understood? Not frame. There is no external load on that beam. This must be 6.81 downwards. This must be 6.81 upwards. Are understood? So that's it. So now comes to this value here. You consider this is a joint equilibrium. This is a joint equilibrium. 6.81 upwards, 1.13 downwards. So remaining is what? Remaining 6.81 minus 1.13. So 5.68. How which direction? Bottom. 5.68. So now it's in equilibrium. Now it is in equilibrium. Now it is in equilibrium. 5.68. 5.6. So shear in beam. So this spillway is 5.68 downwards. So this is 5.68 upwards. So if you see that this joint equilibrium, is matching, should match, then only we will proceed. Otherwise somewhere error is happened, we will check it and let correct it and proceed. Okay, now comes to the downwards. See what is here. 34.09 top watts, 34.09 is top watts, and 6.89 downwards, 6.81, so 27.28. so if it should be equilibrium, then this value must be 27.28. Okay, this value is 27.28. Are understood? So it's 27.28, it must be 27.28. Okay, now here what is this value? So next column proceeded. 27.28 plus 1.13 minus 5.68, it's 22.73. here you will check here 28.4, 5.68 must be it's 22.73. okay, it's 27. Then are understood? That's it. You may also check previously, I forget it, it's 39.09, 5.68, 28.4. these are the axial force in the column. If you check sum of these two, you will get 34.0. what is this value meaning? The total forces of vertical direction is equal to 0, because there is no vertical force in the system frame. So these values must be equal to 0. 28.4, 5.68, 34.09. you may check before entering to the free body analysis. You may check here only, then only proceed. Okay, so that's it. So now shear in beam is over. Shear in beam is over. So now you can calculate bending moment in beam. So if you check this is the beam, you may consider this is a beam. So what was the shear? 6.81, here 6.81. so what are the bending moments? So 6.81, this length is the 4, this is the 4, this is the 4. These are the forces. What is the moments? 6.84 multiply with 4. So moment should also be main. See, if you see this is, if it is this direction, means the moment is happening like this. So you should counterbalance, like this. So moment will come this value this side. Sir, only one side is sufficient to balance, but we assume, again I will say, we assume a point of counterflexure at center. Point of counterflexure at center means both sides has a equal bending moment and in the same direction. So this is, if you consider M, this is also M. A bending moment acting at both ends in the same direction and is equal. Counterbalance those shear. When will happen? This will happen when the point of counterflexure at the center only. So in cantilever beam also we assume a point of counterflexure at the center, then only it will acceptable. So we assume point of counterflexure at center here also. Okay, so now consider what is the value of M. 2M equal to V into distance. So M equal to V into distance by 2. So what is that value? V is 6.84, distance is 4, divided by 2, 2 times. 6.81 multiply with 2, 6.81 multiply with 2 is 13.62. So this is value is 13.62. The direction is here. Are understood? Counterbalance. This will come this direction. 13.62. So I will write 13.62 here. 5.68 multiply with distance is again 4, divided by 2. So 2 times 5.68 multiply with 5.68 multiply with 2 times 11.36. So here it's 27.28 multiply with 2, 54.56. Here 54.56. Here it's 22.73 multiply with 2. Here 45.46, 45.46. So now we will calculate bending moment in column based on equilibrium. I will show you. So here 13.62. So to maintain equilibrium in the joint, it is a clockwise 13.62. It's anti-clockwise of 13.62. Understood? If it is 13.62, we assume point of contact flexure at the center of column also. So at both ends we will get the same bending moment in the same direction. Okay, so it's a anti-clockwise 13.62. Here also we will get 13.62. We will assume point of contact flexure at the center of beam and column in portal frame method, in cantilever method also. Okay, then here 13.62. Now it comes to here 13.62 is in clockwise, 11.36 is in clockwise. So to maintain equilibrium, how much? 13.62 plus 11.36. 24.6898 is anti-clockwise. Understood? 24.98 is 24.98. Here 11.36 clockwise, it's anti-clockwise. 11.36, 11.36. That's it. Now comes to this joint. Okay, so what is that value? 6.81 is in anti-clockwise, 54.56 is in clockwise. So to balance, how much? 47.75 is in anti-clockwise. 47.75 here, here also 47.75. So here, see next, 54.56 is in clockwise, 45.46 is in clockwise, 24.29, 24.98 is in anti-clockwise. So remaining is 75.04 anti-clockwise, 75.4 is anti-clockwise. Now comes to here 45.46 anti-clockwise, 11.36 is in anti-clockwise. So based on the equilibrium equations, we will calculate the bending moments in columns. So here is 34.1, here is 34. Now it's then end of bending moments in columns. End of bending moments in columns. Now comes to the shear in column. How can you calculate shear in column? See. So take this as an example. I will show you. So what is that value? 13.62. 13.62 here, 13.62 here. Height is 4. 4 no? So 4 is the height. So how can you calculate shear? Same, you can just imagine it's like 13.62, 13.62. Okay, that's it now. So you can imagine, just imagine. How can you get it? Same, it's a m, you can get this, you can get this v. So v into distance equal to 2m. So V is 2m by t. T is for m by 2. M by 2. So moment is 13.62 divided by 2. Which direction? Which direction? See, this is the direction to counterbalance those moments. So here this thing, here this thing. Okay. So now comes to calculate 13.62 divided by 2 is here and here. So what is that value? 6.81. 6.81. Here it is 24.98. 24.98 divided by 2 is, so here this direction, this direction. What is that value? It's 24.98. 24.98 distance of this 4 divided by 2. So 2 times. So 24.98 multiply with 2 divided by distance 4. So divided by 2. So what is that value? It's 12.49. 12.49. Here it's 11.36. 11.36 divided by 2. So this direction, this direction. What is that value? 5.68. 5.68. That's shear. Shear in the column. You may write like this. This value. This. You may write, but no need, because that's the point of contracture. Only shear is transverse. That's 5.68. This is also 5.68. No need to write it. I will just show. Okay. So downtime. It's also a 4 meters. So 2 times of movement divided by length. So length is 4 meters. So 2 times divided by 2 divided by 2 will come. So here is 47.75 divided by 2. So 23.87. 23.87. Here 75.04. Here this direction 37.52. 37.52. Here is 22.73 divided by 2. 11.36. 11.36. Okay. Now everything is over. Everything is over through equilibrium equations. One thing is remaining, that's a bending, see, axial force in beam. I will show you axial force in beam. So see, what is the axial force? Transverse force is 25. So 25 must be present in this joint. 25 must be present in this joint. Already what is the value? Already we have 6.81. Already we have 6.81. So 25 must be there. So what is the remaining value? 6.81. 18.2. Okay. So now I will add 18.2. So now it's 25 is completed now. So now giant has a 25. Then sir, but this giant has 0. Okay. So to maintain equilibrium of this beam, 18.2 must be there here. Then only the beam is in equilibrium in all directions. 3 directions: transverse, axial, and bending. 6.81, 6. Vertically equilibrium, horizontally 8.2, bending momentally 13.62, 13.62. Okay. So now comes to the next. Here see, the giant has 0 force. So it's in this direction 18.2, in this direction is 12.49. What is the remaining value? 18.2 minus 12.49. It's 5.71. 5.7. So this is a 5.7, here also 5.7. You can check it. What is the value here? 5.68. Maybe approximate 5.7. You will get it's almost correct. So here is 5.7. It's compression. See the this is in compression. This is in compression. I already said that all beams should be in compression. There is no way, there is no chance to in tension. Now comes to this joint. It's what is the load here? It's 50. Already it has 23.87 this direction, 6.8781 this directions. To maintain a 50 at the joint, how much force and how which direction? 6.81, 17.06 minus 50, 32.94. So you should maintain 32.94. So then if you see, calculate 32.94, 23.87 plus minus 6.88, you will get 50. That's it. So now it's also 32.94 compression. Now comes to the, what is the 32.94 this direction, 12.49 this direction, 32.94 plus 12.49 minus 37.52, 7.91. Compression. Just check 11.36, 5.68. 5.68. You should get 5.68. So you may check it as 32.94 plus 12.49 minus 37.52, 7.9. So this value must be is in 5.68. The value must be is in 5.68 because this is 11.36 is a 5.68. So that's also value of 5.68. Understood? So somewhere is 7.91. We got 7.91. It's a somewhat large error. Somewhere it happened. The error of somewhere it's 2 is a big error. You can check it. Otherwise the problem is over. Okay, you may check it is where the error happened, but the problem is over. Okay, now you may draw bending moment diagram, shear force diagrams, like put a center of point of contact flexure. You may mention the bending moments. You may mention bending moments. Those bending moments diagrams are over. And shear is equal throughout it's equal. So what is the values? It's 23, somewhat higher. 23. Here what is the value? You may check the value. So here also shear is equal throughout the spans. That's it. Bending moments and shear force diagrams are over. Okay, that's it. That's the problem. Okay, got it.